In the last video, we wrote our fraction class and we defined a bunch of operators that allow fractions to be used as if they're numerical data. So we're now able to write with my fractions, x is 6 over 10 and y is 1 over 6. I can write things like x plus y and y plus z, and then x times y. Between videos, I've made one addition, which is I've observed that there are some fractions that just seem inherently sort of unnatural. So if I write negative 3 over negative 6, well, we might notice that's just 3 over 6. So why bother with the negative 3 over negative 6? And then similarly, if I have 3 over negative 6, that looks a bit weird, doesn't it? I mean, that is valid, but it looks a bit weird. We're used to putting something like negative 3 over 6. So I've added some logic in the constructor for fraction that requires the denominator to always be positive. So what it does is, if you pass in a negative denominator, it just takes the negative sign and moves it to the numerator. So in this case, for the first fraction here, negative 6 as the denominator isn't allowed. So what it does is it first negates the denominator, so it pulls off the negative sign, and then it negates the numerator to compensate. So in this case, that results in 3 over 6. If you give me 3 over negative 6, then we negate the denominator and then negate the numerator and get negative 3 over 6. Hopefully that's enough of a justification that this doesn't do anything to the actual, like the real meaning of the fraction, but it does have the nice effect of making the negative sign appear in a consistent location. The real point of the video, though, is to address a different problem that came up in the previous video, which is that although this is valid, it is producing correct results, sometimes they can be unwieldy. So there's 46 over 60. And we stare at that and say, you know, if I were writing this fraction down myself, I might not write it this way. I might write it in lowest terms. So 46 over 60, as it turns out, is 23 over 30. Because both 46 and 60 can be divided by 2. Okay, and maybe this fraction looks a little bit less weird. Similarly, down here, I've got 6 over 60. And I stare at this and say, wait a minute, both the top and the bottom are divisible by 6. If I do that, then I just get 1 over 10, which I think makes a lot more sense to me. Typically, when humans want to work with fractions, we like putting them in lowest terms, and the lowest terms we can come up with. What I want to do in this video is write some logic to do that. Now, to be clear, this is not so much an exercise in operators. It's something we need for the operators to return nice, clean results, but it's mostly just sort of an algorithms thing. It's just sort of an extra task that sort of shows up in the middle of this larger application. So my two tasks are as follows. First, I want to create a member function that takes that I run on a fraction. So I could call on the fraction x. I could write x.lowestTerms. That's going to return a new fraction object that takes the numerator and denominator of x and expresses them in lowest terms. Another way of addressing this is I could say it's never allowed for a fraction to not be in lowest terms. So 6 over 10 is 3 over 5, for example. I would require that every fraction always be in lowest terms. I don't think I like that for now. For now, if you want to put 6 and 10 into a fraction, I will let you have the fraction 6 over 10 if you want. But if you want, you can then ask to have that fraction translated to be in lowest terms. So you have the option of doing it. And I'm going to do that via a member function. The second task is to modify the operators so that when you perform operations on fractions, the result will always be in lowest terms. Okay, so the first step, of course, is defining my function that puts the fraction in lowest terms. So I'm going to do that up here. It's going to be a member function of the fraction. And I'm going to write the beginning of it, and then we have to sort of derive what it means to put things in lowest terms. So I'm going to call fraction lowest terms. And it's not going to modify the current object. It's going to return a new fraction that has been expressed in lowest terms. So I'll write just some stuff to start with here. I'm going to make a new fraction object called result. And for now, I'll just set it to be the numerator and denominator. Then I'll return it. And our goal is to figure out how I reduce this fraction to lowest terms. To do that, I'm going to talk about what it really means to put a fraction in lowest terms. So let's look at the fraction 16 over 20. If you, I guess, work with fractions on a in a math course or something, you're probably used to putting things in lowest terms. You've done it before. It's covered by a prerequisite of this course way back in high school or whatever, elementary school. But maybe we should go through that a bit more formally. So what I could observe is both 16 and 20 are divisible by 2. So I could rewrite the fraction as 8 over 10. I could then observe that 8 and 10 are both divisible by 2, and I could reduce the fraction to 4 over 5. This is probably the way you do things like this. You look for some common divisor and then use it. But I want to justify formally why this works. It's not going to surprise anybody, just so that we know that we've got a good footing here to actually do this in the code that we're about to write. So 16 over 20. Well, okay, 2 divides 16 evenly and 2 divides 20 evenly. I could then write 16 over 20 as 2 times 8 divided by 2 times 10. And I could split those off into the fraction 2 over 2 times 8 over 10. And then I could observe that 2 over 2 is just 1. So I could just erase this and write it as that, which is why 16 over 20 equals 8 over 10. That's why I'm able to do that simplification. So my goal then, if I would like to simplify fractions to be in lowest terms, is to find numbers that divide both the top and bottom. And there's one other note I want to make. So if we go back to 16 over 20, I could divide both by 2, but I could also observe that both 16 and 20 are divisible by 4, and then divide 16 by 4 to get 4, and 20 by 4 to get 5. And then I would be all the way at the end in only one step. And in fact, if you want to reduce a fraction to lowest terms, the easiest way of doing so is to look at the numerator and denominator and compute their greatest common divisor, the largest integer that divides both numbers evenly. And in cases where there is no number, like in cases where they can't both be reduced any further, the greatest common divisor would just be 1, because 1 does divide 4 evenly and 1 does divide 5 evenly. So what I'll do then is I will compute the divisor, and I'll say, I guess I'll write a function to help me with that. It'll compute the greatest common divisor of the numerator and denominator. Okay, and then I will just divide both of those to reduce the fraction. So I'll compute the divisor, divide the numerator by the divisor, divide the denominator by the divisor, and then return the resulting fraction. Okay, so now how do I compute the greatest common divisor? So a few things. If you've taken a course like Math 122, you would probably be familiar with something called the Euclidean algorithm, which is a way of computing greatest common divisors. You might want to use something like that. There are also a few other tricks you could use. It turns out we're going to see there's actually a standard library function that does this for us. And in the next video where I use fractions, I'm going to call the standard library function. For today, though, I want to prove a different point, which is that even if you have no idea how to do this, I'll bet we could come up with a basic algorithm without knowing anything. We don't need to take Math 122 to be able to compute the greatest common divisor. So I've written this as a call to a function. I'm going to go up here and write a function to do this. Int GCD, and it takes 2 values, A and B. And I guess I'll write a quick blurb about what it does. So GCD of A and B, compute and return the greatest common divisor of A and B. The greatest common divisor has to be an integer. Here's the way I'm going to attack this. So I've got 16 and 20. What I'm going to do is I'm just going to try every single number, starting with, we'll use 16 here, because obviously the greatest common divisor can't be any larger than the smaller of the two numbers. So if I pick one number at random, even if it's the larger one, I could just start at 16 or start at 20 and work my way down and just keep testing as I go down, does this number divide both things? So maybe we'll start with 20. I'm going to start with the number 20. And you could, with a small modification of what I'm going to write, you could make this run a little bit faster by choosing as your starting point the smaller of the two inputs. But it turns out you could use either of the two inputs and it's still going to work. So I start with the number 20. And then I ask the question, does this evenly divide both numbers? No, it doesn't. Okay, what about 19? Nope. What about 18? Nope. What about 17? And I just keep trying them. So 16 doesn't divide 20. It does divide 16. 15, nope. 14, nope. 13. And then I keep going. I'm actually going to go through this all the way through. Okay, 7 doesn't, 6 doesn't, 5 doesn't, and then I try 4, and it does. 4 does divide 16 evenly, and it does divide 20 evenly. So 4 is my greatest common divisor. So all I do is I start from one of the numbers, and I just walk downwards until I find a number that works, until a number divides both things evenly. Okay, so we'll try that. I'm going to start with my value. I'll call it n. We'll just start with a. And then I'm just going to keep going as long as n is greater than 1. I actually used a C-style initialization there. Better cut that out. And so at each step, I'm going to ask the question. Does n evenly divide both a and b? Okay, so if a modulo n is equal to 0, that means that a is evenly divisible by n. And if b modulo n is equal to 0, that means both a and b are divisible by n. In that case, it sounds like n is my greatest common divisor, so I return it. And then otherwise n minus minus. I just go down by 1. At the end, if I get out of the loop and I still haven't found anything, that means I have two numbers that do not have a common divisor other than 1. So 6 over 7, for example. 6 is divisible by 1, 7 is divisible by 1, but they're not both divisible by anything else. So their greatest common divisor is 1. I'm going to write that like this. If I tried to, you could maybe look at this and say, yeah, you could just have the loop keep running until it goes down to 0, and then it would return 1. The compiler might complain because it wouldn't understand that, so I'm going to write it like this. So if n gets down to 1, we just return 1. Okay. And then I've got my function lowest terms, because lowest terms just calls GCD to compute the greatest common divisor. And then it returns the result of dividing the numerator and denominator of my fraction by the greatest common divisor. So we'll give that a try. All right, so let's take a look. So I've got down in main, I've got a test call to the lowest terms function. So remember that I don't get the fraction in lowest terms unless I do the fraction dot the lowest terms function. It doesn't get automatically converted, although I could write it to do that. And I print that out, and I notice here x is 3 over 5 in lowest terms, which is a good sign. It sounds like I was able to reduce my fraction to lowest terms. The second task then is to adapt all of my operators to always return a fraction that's in lowest terms. That part, fortunately, is pretty easy. All I do is go find my operators. There we go. And there we go there. There we go. There we go. I just return the result dot lowest terms. I convert the fraction to lowest terms as I return it. I should also notice between videos, I did also add this less than operator to compare if two fractions, if one fraction is less than another. We'll come back to that later. That'll show up in a lecture later. But and there's a derivation given here quickly. It's the same style of derivation I would have had to create when I added two fractions together, but I deemed it not terribly salient for recording a video about. But if I wanted to put a bunch of fractions in a set and have them maintain numerical order, that would be a big deal. And take a look at the posted version if you want to read that comment in more detail. Okay, so I've just converted, I've rewritten my operators to convert every fraction to lowest terms, and now I notice when I try and multiply x times y, so when I try and compute x is 6 over 10 times 1 over 6, well, it originally came out with 6 over 60, which is not in lowest terms. If I now scroll down to what I have as a result of the change, I now get 1 over 10. My fractions are now being returned in lowest terms. They are looking a lot more like the type of output I would expect out of operations that legitimately work with fractions. Okay, so I mean, I have more examples involving fractions in future videos. We're now actually ready to go back to that problem at the beginning of the previous video, which is this contrived exercise where I do a bunch of arithmetic. I'm now using fractions instead of doubles for this. So I've got my fraction x, which is this number over 1. I've got my fraction y, 1 over 5. I've got z, which is 0, but we'll write 0 as being 0 over 1. And now I want to compute x plus 5 million times y, all minus x. And we saw in the previous video that if I do this with real numbers, I get some strange value that's off by a little bit. So instead of being exactly 1 million, it's 999,999, which is a bit spooky. We sort of don't want that. We don't like the idea of our numerical calculations being off. Here, I'm going to do the exact same calculation I did before. This code is line for line identical to what I had in the previous video with doubles, but now I'm using type fraction. And partially, I'm doing this to prove that I have a great abstraction here. The fraction type behaves just like a number. There's one last detail, though, which is at the end, when I want to convert it to a real number, I do have to call dot to real. A future video will talk about how I could even eventually write it like this. I could actually make z behave exactly like a double value, except how the arithmetic gets done. We're not there yet. I want to run this, though, to show off that this does give the exact result that I want. So that, I mean, beyond that the fraction type is a clever toy, that it actually can do work. It can actually perform legitimate calculations for us. And there it is. The result that comes out is 1 million. You might have noticed it took a little bit longer to run. That is because the fraction object requires a bit more work than the built-in floating point calculations that the processor can do for us. But it didn't take that long. I was able to do 5 million computations pretty quickly. And I got the fraction 1 million over 1, which when converted to a real number is just the number 1 million. So I was able to get around those rounding errors that occurred with double and float values by defining defining my own rational arithmetic type. And once it was defined, and it was a bit of a pain, once it was defined, I could use it just like any numerical type because of the features the language gives me to abstract away all of those details like how do I divide two fractions or how do I add two fractions.